Hello, this is Dr. Gardner. I thought I would record a short tutorial on how to perform dimensional analysis problems. We will apply these types of problems to converting units on our calculations. And sometimes you might hear dimensional analysis described as the factor label method or the unit factor method. We'll see that it really helps us keep track of converting one unit to another, especially we're going to see it with respect to converting from the English to the metric system or the metric to the English system, or it's very useful in converting from one metric unit to a second metric unit, as we will see. Now, the first part of this tutorial will be just a little bit of background relating dimensional analysis and how it relates to what you have learned when you had taken math courses early in life on multiplying fractions, as well as relating to keeping track of units in algebra with respect to x's, y's, z's, the variables that we normally look at, and you'll see how that relates to our units on our numbers in the sciences being treated as if they're variables when I convert one unit to another. Now, the second part of this tutorial will look at converting a single unit into another unit. And then we'll consider when we might have to use two conversion factors, let's say in scientific notation, to convert units. And then I plan on recording a second tutorial that will be also posted. The second tutorial, when you open that one, that will look over more advanced unit conversions with multiple conversion factor steps, or converting numbers with 2 units, which you could use what you learned there skill-wise to convert numbers with more units than that even. So right now I'm going to focus on part 1, converting single units and the background related to that. So let's consider if we were looking at fractions. We are going to be treating all of our numbers as if they're written as fractions, and realizing that if I write any number multiplied by 1 or divided by 1, it's going to be the same number, but I may go ahead and use that to apply to writing fractions. But first of all, let's consider if we had the following fractions we were multiplying. Let's say I had 2/3 that I was multiplying by 1/2. Now I want you to notice we could look at the 2/3 of the 1/2, and when I'm multiplying those, we could see that the 2 in the numerator at the top of the first fraction will cancel the 2 in the denominator in the second fraction, the bottom of the second fraction. So I could cancel those two out and see quickly that my answer would be 1/3. We're going to see how this can also be applied for canceling out units when we're doing conversions from one unit to another. When we have a unit that's in the numerator being multiplied by a unit in a denominator in a conversion, that would cancel those out to provide a new unit. So we'll see how this relates to simple fraction multiplication. Now let's see how that also relates to algebra. So let's say I have 60x over 1y times 2y. Let's write this as some simple fractions to keep track of what's happening with my variables x and y here. So here I've written 60x in the numerator, and the denominator I'm putting 1y. Now I'm going to multiply by 2y, but I want to write it as a fraction. This will help me keep track of everything if I'm writing them all as fractions during conversions. So I'm going to have 2y over 1. That didn't change the value of 2y if I divide it by a 1, but we've expressed it as a nice, neat fraction. And you can see now that my variable of y should cancel. Right? I have in my denominator in the first fraction a 1y. I'm multiplying in the numerator a 2y in the second fraction. So you should be able to see the y's cancel quite simply. Now this would allow me to convert that unit if I needed to. So I'll show you a very simple example similar to this where we have units rather than x and y's. Okay, so my answer here would be 120x over 1. Now I can simplify that and just write that as 120x because I know any number divided by 1 is just itself. So really what I did here was cancel out the y's. If those are units, we could have then potentially canceled those units out. So let's work a very similar problem where instead of x's and y's and the variables I'm very comfortable with working with in algebra, I'm using actual units in a mathematical problem in a science course. Let's say that I have the following question I'm trying to answer. If you're traveling at 60 miles per hour and you want to know how far you will travel in 2 hours, now you probably could do this in your head fairly simply, but you'll see soon we'll start working problems that are a little more challenging to keep track of in your head, and you'll see writing these fractions with what we call the dimensional analysis method or the factor label method will help us keep track of converting units. So let's write the 60 miles per hour as a fraction. So I have 60 miles over 1 hour, And then if I want to multiply by my 2 hours, I can write that as a fraction if I just put it over 1, and that won't change its value. So I can take 2 hours over 1, and I can multiply that. Now, can you see, just like our y's canceled on the previous problem when we were comparing it to algebraic variables, can you see my units would cancel for hours here, shown in red? So my 2.0 hours, the hours as a unit will cancel with the 1 hour when I had written the 60 miles per 1 hour. And then I would see my answer could be expressed as 120 miles over 1, or just simplified to 120 miles. So this is very similar to what I just showed you with the x and y algebraic variables. Only thing we've done different is we replaced those algebraic variables that you're very comfortable with seeing in algebra courses with units as variables, but they work the same way. The factor label method, dimensional analysis, shows me I can cancel units just like they are my variables, my x, y's, or z's in algebra. Okay, so I'm just applying that to help simplify keeping track of units in problems. Now, I require in my course that you write out your answers with units. And I would prefer you put a box around your final answer if that's the one you want me to grade. On a test, you might have multiple possible times you tried to work out the problem, and there's one that you felt like you did the best. Box that one you want me to grade so I know that was the answer you decided on. I won't try to guess if you don't box the answer. I may just pick whatever I think was your final answer if you don't indicate the correct answer. So here I would box 120. I would write the miles there. I know I would get a point deduction if I didn't show the correct units at the end. So I'm going to want to always write my units. In fact, if you show me your work written out with this method, showing everything as fractions and canceling units out, and you show your final answer with the correct units, usually you'll catch the error before you even show it to me. But if you bring your work to me, I can quickly find your error if it's set up correctly the way I'm teaching you right now. So let's try writing some conversion factors using my units as variables. So now if I want to write some conversion factors, let's consider a conversion factor we might know. So if I want to convert from length in the English system to the metric system, it might be useful to know that 1 inch is 2.54 centimeters. Okay. Now there's two possible fractions I could write with this as a conversion factor to indicate ways I could convert units. So the first possible fraction I might write would have in the numerator 1 inch and the denominator 2.54 centimeters. So I could write it as 1 inch over 2.54 centimeters. Now that's only one of two possible fractions I could write here, right? Now what I would want to do is if I want to convert from centimeters to inches, this is the fraction I would want to use because then it would cancel centimeters out and leave me inches as my final unit. So that's the one I use for converting from centimeters to inches. If I want to use the inverted fraction here of 2.54 centimeters over 1 inch, well, this is the conversion factor. This is the fraction I would use in the dimensional analysis to convert from inches to centimeters. Okay, so I have to be able to decide which one of these I need to use, and by writing my units down, I can see that I would cancel out the units to the number that I'm trying to convert from and provide the units in the end that did not cancel to the units I'm trying to convert it to. So you'll notice that the unit I'm trying to convert it to is always on the top of the fraction. So if I'm trying to convert from centimeters to inches, the inches would be on the top of the fraction. If I wanted to convert from inches to centimeters, centimeters would be on the top of the fraction. Okay, so let's apply this to a problem. Let's say I want to convert from centimeters to inches. Which one of these fractions do we want to use? Okay, keep that in mind and we'll see it show up here in just a second. So I'm asking the question, how many centimeters are in 8 inches? Okay, so I need to think, what are the useful conversion factors that I should know to help me perform this conversion? So I'd write down, when I begin the problem on my piece of paper in my homework notebook, I start writing down the conversion factors that would be useful for the problem. So here I would think, well, 1 inch is equal to 2.54 centimeters. I look to see if that would help me convert from centimeters to inches for the original question, and I'd say, yes, indeed, that would be the correct conversion factor I need. This is a fairly simple conversion. It should only take one step to convert the units. And so I need to decide, okay, well, what are the fractions that might be useful here? Well, I could have 1 inch over 2.54 centimeters as one possible fraction I could write, or the other fraction we had written was 2.54 centimeters over 1 inch. Now, if you recall, I said that the units you are trying to convert to should be in the numerator, in the top of the fraction. The units you are trying to cancel should be in the denominator here in the bottom of the fraction. So let's see how that works when we set up the dimensional analysis. So I'll write down the number that I want to convert from first. So the 8 inches, I make sure I write my units down with that. So I write 8 inches. I write that as a fraction, so I just put it over 1. Okay, that won't change its value, but it sets everything up as a fraction in the dimensional analysis. Now I'm going to multiply by one of my fractions that I produced from the conversion factor. Okay, so I need to decide which one. You notice you want to cancel inches out, so I want to put inches in the denominator. So I pick the 2.54 centimeters over 1 inch, because I would see if I do that, the inches would cancel with respect to my fractions I'm multiplying. So I'd end up with 2.54 centimeters per 1 inch. Okay, so I'd use the second of my two fractions that I could have produced from the conversion factor. So I always check, am I going to cancel those units out? Now when students forget to write their units down and they decide they want to work something quickly and they don't write the units down, that's when they'll invert these accidentally and have the wrong answer. So units will be your friend if you always keep track of them. So I can see here then, my inches should cancel, just like when I was seeing my y's cancel in my algebraic variables, except here my variable are the units of inches. And I'm going to end up, instead of having x as a final variable, I'm going to have centimeters as the variable that did not cancel. So I take the 8 inches times 2.54 centimeters per 1 inch, and I'd end up with an answer of 20.3 centimeters as I convert my inches to centimeters over 1, and I can go ahead and write that as a number that's not a fraction at the very end. So I can report that as 20.3 centimeters. Very simple once you realize we're canceling units just like they were variables in dimensional analysis. How about we try going the other way? Let's convert from centimeters back to inches. Okay, so here's our problem. I'm going to take 35 centimeters and convert it into inches. Now again, I'd write down the useful conversion factors that I might be able to use to solve this problem. Again, we would use 1 inch as 2.54 centimeters. Two possible fractions could be written with this conversion factor. I could write 1 inch over 2.54 centimeters or 2.54 centimeters over 1 inch, and I have to decide which one of those to use. Now if I'm trying to get an answer in inches, I want that in my numerator. And if I'm trying to cancel units of centimeters, I want that in my denominator here. So I write the number that I'm first trying to convert, 35.0, and I write the units down of centimeters. I put this a fraction over 1. Then I'm going to multiply by the fraction I want to use to convert the units from centimeters to inches. So I realize in the bottom of that fraction, in the denominator, I want centimeters in order to cancel centimeters out. So I should recognize that I want to use this first fraction. 1 inch is 2.54 centimeters. So you notice we're using the reverse fraction because I'm converting units the other direction, from centimeters to inches rather than from inches to centimeters. So I put the 2.54 centimeters in the denominator. Now I'll see my centimeters will cancel. I know there's 1 inch for every 2.54 centimeters, so that's the fraction I picked to use here. Now the centimeters will cancel at this point and leave me with my answer in inches as the only unit that has not canceled out in the dimensional analysis. So I end up with 13.8 inches over 1, or I can write that as just 13.8 inches. So it's very useful to keep track of your units and cancel them this way. This will become more and more important. It's increasingly important as we continue on through the course, as we start to do multiple unit conversion steps and more complex problems. So it really will be useful to practice with these one-step conversions and then start going to more complicated problems and stay in the good habit of always writing your units down, always making sure your units cancel out to give you the correct units for the final answer. If you're very careful with setting these up, you will usually have the correct final answer unless you've written the unit conversion down incorrectly with respect to the numbers. I always say my unit should cancel, and I can usually double check my work and have the right answer in the end. So now we've been looking at lengths of centimeters and inches. How about we consider converting from kilograms to pounds next? So let's convert 81.6 kilograms into pounds. Okay. Now the useful conversion factor that might help me here is to know that there is 2.205 pounds for every 1 kilogram. Now again, I can write two possible fractions for this, right? I can put the pounds on the top and the kilograms in the denominator, or I could show the kilograms over the pounds. So let's look at the two possible fractions I could use. I could write 2.205 pounds per 1 kilogram from this conversion factor, or I could write 1 kilogram for every 2.205 pounds. I have to decide which one of these I want to use. Since I'm converting from kilograms to pounds, the first fraction would be the best, because I want to put the unit that I'm trying to cancel out in the denominator. Okay. So I'd first write down the 81.6 kilograms. I can write it as a fraction. It does not change its value to divide it by 1. I'm just writing everything as fractions to stay in that good habit. and then I can say I'm multiplying that by the conversion factor that will cancel the kilograms out. So I need the kilograms in the bottom of my fraction in the denominator. Okay, so I write 1 kilogram, and that's under 2.205 pounds, so I have 2.205 pounds over 1 kilogram. I can see the kilogram units will cancel, just like an algebraic variable here. So the kilograms cancel. I should have a final answer in pounds now that I've used this correct conversion factor. So I'll see this could be 180 pounds. So we can see that 81.6 kilograms, it would be the same as a person who weighed about 180 pounds in Earth's gravitational field. So I could write that just as 180 pounds here. Okay. Now, what if I want to convert from pounds back to kilograms? I wouldn't use the same fraction for the conversion factor, would I? I would use the inverted conversion factor, that second fraction we had seen. So let's see how that works. So I want to know how many kilograms a 221-pound person would weigh. So I write my useful conversion factor. There's 2.205 pounds for every 1 kilogram. There's two possible fractions I could write. I could write either pounds over kilograms, 2.205 pounds for 1 kilogram, or I could write a fraction as 1 kilogram over 2.205 pounds. Since I'm trying to cancel pounds out, I want the pounds in the denominator, we'll see here in a minute. And since I want kilograms for my final units, I want them in the numerator at the top of the fraction. So let's see that as I set it up. So first of all, I write the 221 pounds down. I can write that as a fraction always, just to stay in that habit that we're using fractions for the dimensional analysis to convert units. And then I can say, okay, I'm dividing by pounds, so I need to use the second fraction that I had based on my conversion factor. So I'm going to have 1 kilogram over 2.205 pounds. I can see the pounds will cancel here for my units to give me kilograms for the final answer. So my pounds will cancel, and I could see I would get 100 kilograms to 3 significant figures for this person. So a 100 kilogram person in Earth's gravitational field would weigh 221 pounds approximately. So that gives me an easy way to make that prediction. So I should be able to convert either direction. I just need to know which of my fractions to use. Recognize that the unit you want to cancel should be in the denominator for the second fraction I write in the dimensional analysis. The unit for my answer should be in the numerator at the top of the fraction. Now let's try converting in the metric system. Let's convert 675 nanometers to meters. So I need to be comfortable with what the nanometer prefix means with respect to the base unit of meters. So the conversion factor I should use would be that 1 times 10 to the negative 9, the meters, would be 1 nanometer. Okay, so I should recognize that from knowing nano for my metric system prefixes. Now there's two possible fractions I might write for this conversion. I could write 1 times 10 to the negative 9th meters over 1 nanometer. Or I could write 1 nanometer over 1 times 10 to the negative 9th meters. Now since I want my final answer to be in meters, hopefully you're starting to recognize that I should have that in the top of my fraction, in the numerator. And then the unit I want to cancel, the nanometers, here should be in the denominator at the bottom of my fraction. So I bet you can predict that you'd want to use the first fraction we could write from the conversion factors. So I start with the 675 nanometers as my initial number with its units that I want to cancel. I write that as a fraction to stay in good habits. And then I'm going to multiply that by one of my conversion factor units, that fractions that will cancel out my units. So I want the nanometers in the denominator. So I have 1 times 10 to the negative 9 meters over 1 nanometer. I can see now my nanometers will cancel just like an algebraic variable here. And I would end up with units of meters. So this would give me 6.75 times 10 to the negative 7th meters. Now I want to ask myself, does this answer make logical sense? Should I have a very tiny amount of a meter if I started with 675 nanometers? You should be saying, yes, that seems true. Right? Because a nanometer is a very small unit, so it should be a very small portion of the base unit of meters. This will help you in case you were to invert your numbers here or write the wrong scientific notation. If you ended up with a very large number for meters, you'd know immediately you made a mistake. Doesn't make sense for the small number of nanometers we have to be a large number of meters. That would be the reverse of the correct logic, so I should be able to check my answers before I ever submit them to my instructor. So you can often catch your own mistakes if you're thinking about whether the answer makes logical sense. Now, if you just merely get the number, write it down, and not think about what it means, you're very likely to miss mistakes. And then you could have avoided that and had a better grade on that problem if you had looked at it and thought, well, does that make logical sense? Here we can tell, yes, a very small amount of a meter would be in the range of a couple hundred nanometers. So yes, this makes complete sense. Now let's say I want to convert from the 6.75 times 10 to the negative 7th meters to centimeters. So I want to go from meters to centimeters now. Now my conversion factor for centimeters, I should realize, well, there's going to be 1 times 10 to the negative 3rd meters, right? 100th of a meter is 1 centimeter. Okay, that's my conversion factor I could use here. There's two possible fractions I could write. I could write 1 times 10 to the negative 3rd meters over 1 centimeter, or I could write 1 centimeter over 1 times 10 to the negative 3rd meters. Now you should recognize you want to have in the numerator the units for your final answer. So I should be looking at the second fraction here. I want centimeters on the top. I want meters on the bottom to cancel out the meters in my initial number that I'm trying to convert. So as I set it up, I take the 6.75 times 10 to the negative 7th meters over 1. And the conversion factor I'm picking should cancel my units out, so I should put meters on the bottom. So I'm going to have 1 times 10 to the negative 3rd meters. 100th of a meter is every 1 centimeter for my conversion factor. My meters will cancel, and that would give me an answer then that would have units of centimeters that had not canceled. So I end up with 6.75 times 10 to the negative 4 centimeters over 1. Or I could just write that as my number of centimeters. Now I can think if that makes sense. We went to a smaller unit, so the number became larger by a factor of 100 here, right? So that makes sense. Let's consider I want to convert from the metric system using one prefix to a second prefix. So let's say we want to convert from 900 nanometers, sorry, 9,000 nanometers, 9,000 nanometers to centimeters. So now we aren't converting to our base unit, so we need to be careful. Most students, as they're first learning the metric system, will not have memorized the conversion factor from nanometers to centimeters. And that's okay as you're beginning. If you know the conversion factors from the nanometers to the base units of meters, and then from meters to centimeters, we can do this problem in 2 steps with what you should know from your conversion factors. So here's my plan. Okay, I'm going to take the nanometers, and since I know the conversion factor from nanometers to meters, I'm going to convert in step 1 from nanometers to meters. Then, since I know the conversion factor from meters to centimeters, I'm going to do a second step to convert to centimeters. Now, some of the students are really comfortable with the metric system, might do this all in one step with one conversion factor between nanometers and centimeters, but the rest of you should probably do it in these 2 steps I've outlined in our plan for the calculation. Okay, so I need to write down my useful conversion factors. If I'm going to do the 2-step calculation that we planned out, I'm going to need 2 conversion factors, 1 for each step. Okay, so my first conversion factor will relate my base unit of meters to nanometers. So 1 times 10 to the negative 9th meters would be 1 nanometer. Okay, so that would be the conversion factor I'd use for that first step. I should recognize I'm trying to convert to meters, so I want to use my fraction with meters in the numerator, in the top of the fraction, and nanometers in the bottom of the fraction, the denominator here. So I chose which fraction I'm predicting I'm going to use. I'm going to check to make sure the units would cancel, though, on that first step. Now, in the second step, I need a second conversion factor. I'm going to convert from the base unit of meters to centimeters. Okay, so I have to know that 1 times 10 to the negative 3rd meters, 100th of a meter, would be 1 centimeter. Then I should recognize, since I'm converting from meters to centimeters, I should be using 1 centimeter over 100th of a meter, or 1 times 10 to the negative 3rd meters in scientific notation. So as I'm doing this, let's go ahead and calculate step 1 first. Let's convert from nanometers to meters. So I take the 9,000 nanometers as a fraction. I multiply it by my first conversion factor. I'm multiplying it by 1 times 10 to the negative 9th meters over 1 nanometer. I recognize the nanometer should be in the denominator here for the second fraction, so nanometers would cancel just like an algebraic variable. And then since I want to convert to meters, I put meters on the top as 1 times 10 to the negative 9th meters. And we'll see that nanometers would cancel. I'll get an answer that's 9 times 10 to the negative 6 meters. That makes sense. It should be a very small portion of a meter since I had nanometers to begin with. And so I could say I have 9 times 10 to the negative 6 meters. I'm right here in the middle part between step 1 and step 2. I converted from nanometers to meters. I want to convert now from meters to centimeters. So let's go to a second slide and do the second part of this conversion. Okay, so I know that I had 1 times 10 to the negative ninth meters was equal to 1 nanometer. We had the fraction we used last time for that. Now we need to recognize 1 times 10 to the negative third meters is equal to 1 centimeter. So a hundredth of a meter is equal to 1 centimeter. So my conversion factor here will be 1 centimeter over 1 times 10 to the negative third meters. Now there's other ways you could write this. Some students might write 100 centimeters per 1 meter. That's the same ratio for the relationship between the units, and that would also be okay as your conversion factor. Right now I'm just focusing on scientific notation and understanding what your prefixes in the metric systems mean. So I'm focusing on the ones we defined with the metric system to begin with. So okay, I'm going to take my value in meters that we calculated in step 1 on the previous slide. So I take 9 times 10 to the negative 6 meters as a fraction. Now I'm converting from meters to centimeters. So I need to use a fraction that will have meters in the denominator and centimeters in the numerator at the top of the fraction. So I'm taking 1 centimeter over 1 times 10 to the negative third meters. I can see by putting the meters in the denominator here, I will cancel out my units of meters, and I'll end up with an answer in centimeters. So I converted to 9 times 10 to the negative third centimeters as my final answer. So this is my second step in the calculation of my final answer. So I just break it into slow, simple steps. I write my answer for every step as I'm keeping track of them carefully. That will help me get the correct answers for these multiple step unit conversions that I might have to write out. Now we could do this all in a single calculation. So once you're comfortable, we could do all of these conversions all on one page. So let's say I want to convert from the 9,000 nanometers to centimeters all on one calculation without stopping in the middle after step 1. I still need my conversion factors from meters to nanometers and my meters to centimeters that we have been using. But let's see how I would set this all up to do the calculation all at once. So I call this kind of daisy chaining the conversion factors one after the other without stopping in the middle. So I'd start with the first number that I want to convert from and do these conversions all with one calculation. So I'm starting with 9,000 nanometers as a fraction. Then I'm going to convert from nanometers to meters, so I use my 1 times 10 to the negative 9 meters per 1 nanometer. That would get me to the first calculation step, but I don't have to stop there. I don't even have to write this down. I could go ahead and in my calculator do this all at once. So for my second conversion factor to cancel out nanometers in the first step, now in the second conversion factor to cancel out meters and go to centimeters, I can write that fraction down as a conversion factor. Meters will cancel to give me centimeters. I can see all my units cancel out to keep track of things. And in my calculator, I'm going to multiply everything in the top of the fractions, divide by everything in the bottom of the fractions. So I'm going to take 9,000 nanometers times 1 times 10 to the negative ninth meters times 1 centimeter, divide by 1 nanometer, divide by 1 times 10 to the negative third meters, just divide by everything in the bottom of the fractions. We would see then my final answer would be 9 times 10 to the negative third centimeters. So once you're comfortable daisy chaining, putting multiple conversion factors together in one calculation like this, you can find you can do these types of conversions fairly rapidly. Okay, so keep practicing these. This is going to be the last example on the first part of our tutorial with dimensional analysis. I'll be recording a second tutorial with some more complex dimensional analysis conversions of units, such as when we have numbers with multiple units that we're converting. So keep a lookout for that second tutorial. Thank you.